now look, the reason I'm talking about big numbers like that, what I want to now do is start to look at energy in terms of major usage. And so here's a slide I haven't updated it lately, but it was updated to essentially 2000. The U.S. basically uses 100 ectajoules per year. So that's why I was highlighting ectajoules there on that earlier slide. So it's 100 times 10 to the 18th joules per year. And if you look at it, fossil fuels back 8 or 9 years ago by now, 10 years ago by now, they accounted for nearly 86% of it, and I don't imagine that number has changed all that much since then. And you'll see there's 23 coal, 23 of natural gas, and 40 of petroleum. There's been about 100 nuclear plants running in the U.S. for the last 20 years, and there's been no new additions, and so what you can see from this little column is it's actually been improving efficiency on all the run those all along to the point they're up to getting 8 ectajoules from those. And the renewables, which are mainly essentially hydroelectric and biofuels, account for about 8%. I don't know what this is now, but I don't expect it's gone up by more than a factor of 3 or something like that. Still significantly less than 1%. So that gives you the scale. I mean, the real thing is that it's 100 times 10 to the 18th. So now if you want to think of having it, what I'm really looking at this from a point of view of if I want to do something now that has an impact of having an impact like 1% or 10%, you know, if we're talking about things, and I'm going to talk about in a minute about sequestering carbon dioxide, which is one of the big topics being discussed actively in large parts of the world right now, including Western Canada, and Obama's government has got a fair amount of effort going on to that sort of stuff. What I suggest is that when one starts to discuss these issues, one should be discussing it in terms of having an impact on numbers like this. And so if you can have an impact at the level of 1%, it's 0.2 ectajoules at a level of 10%, which is now becoming actually significant if you start to try to do something at that level. Then you're talking 10% of 23 or 2.3 ectajoules. So those are when you start to actually work with numbers that might make a big impact in terms of, say, carbon dioxide reduction. So, but what does all that mean? So you look how much of a product must be, again, for just basic arithmetic. We'll skip through this fairly quickly. But basically, you just do the math from 10 to the 18th and our 4 times 10 to the 5th joules per mole, work your way down through it, through the 12 grams of carbon for each mole of coal, and an ectajoule ends up with something like about 2.5 times 10 to the 13 grams each year. And that's about 10 electric plants. So that's 10 large electric plants, and that's 10 to the 18th now. Now we start to look at this from the point of view of carbon sequestration, which I was just talking about. How do we get rid of that carbon dioxide, which is an item of very active discussion in global warming and all these other aspects of using coal for energy. So we talk about sequestering carbon dioxide into deep underground reservoirs, so permitting so-called clean coal. So let's make an estimate of this plant, what sort of sense it actually is. So we start with a thing, let's make an estimate to bury 10% of the carbon dioxide produced from coal in the U.S. And I pick a number like 10% because, again, it's one of those, you want to make an impact, somewhere in the 1% or 10% gives you, something that actually does have an effect. Doing 1/10% or 100% really has very little impact. It's a demonstration project, but it has no measurable difference. So now we look at that number we pulled off from that previous slide of the total amount of coal being used, and you come up with, try to do that, so that's the order of 2.5 times 10 to the 18th joules of energy from coal in a year. So we put our 30,000 joules per gram of coal, and as I say, you can look this up, on one of your various websites and stuff like that, but we've already done a very simple calculation, and we can do that ourselves. In the simple calculation, to give us the order of 3 times 10 to the 4 joules per gram. We now start with our 2.5 times 10 to the 18th, which is our 10% effect, and we find that we're basically burning something like 10 to the 14 grams of coal to produce that. Now we remember again that 12 grams burns with oxygen to become 44 grams of carbon dioxide, and it also produces, in the process of burning, it produces 22.4 liters of NTP, and that's basic relationship that I mentioned near the beginning of the talk. And so, what does that actually lead to? And it leads to something like 0.4 gigaton, which is, they tend to talk about carbon dioxide in units of gigatons, and the order of 2 times 10 to the 14th liters of carbon dioxide, again, at standard temperature and pressure. And sequestering it, we would probably pressurize it, but nonetheless, that's the sort of scale that's being produced. Now, to put it in terms of how, actually, can we do something with it? We'll do a visualization experiment on that. We do 10 to the 2 times 10 to the 14th is equivalent to 2 times 10 to the 11th cubic meters. And you sort of divide that down into something like 100 kilometers by 100 kilometers by 20 meters deep. So if you look at that in terms of volume of something that's recognizable, it's basically the area of Georgian Bay of 15 meters deep. And we looked it up, it's essentially the equivalent volume of half the volume of Lake Erie. That's being produced at 10% of the year U.S. consumption of coal right now. That's the amount of carbon dioxide that's being produced. So, we look at the visualization. Here's Lake Erie or here's Georgian Bay. It's basically that area to 15 meters deep. That much volume to put that carbon dioxide in some sort of underground pit yearly, every year, safely and securely, from just 10% of present U.S. usage of coal. And you can ask a very nice question about where will you actually store this. If you look at the North America, if you're producing this stuff, you don't really want to ship it large distances because it's going to be shipped in a very safely built piping system at a higher pressure, which means it's a pressure vessel type of plumbing, which is expensive. Well, you look along North America, most of the coal is actually used. If you go from the Mississippi Valley somewhere along here up through this part region, but anybody who looks around at the geography we have around here, you realize that these sort of regions, and if you drive down to the States, an awful lot of it is basically this hard shield rock that we have now. And the idea of trying to find volumes, permeable volumes below that, where you can put the volume of CO2 equivalent to half of Lake Erie's volume yearly, is very hard to believe is doable. And shipping it miles out west where there's already oil wells and stuff like that, where they talked about placing CO2, probably not economically feasible. And so that's basically what I've said in this slide. I preempt it myself. Half the coal is used in eastern North America, more than half of it. Hard to find a place to put it. Can you store it as liquid CO2? Well, you can, but it's above 10 atmospheres. You really have to get at your higher pressure. You've got to look at safety issues. Carbon dioxide kills all mammals very quickly if it gets at a certain concentration. So if you start trying to bury it at high pressure in an underground cavern, if it leaks and it starts to accumulate, you've got a severe safety issue to deal with. So when you look at the scale of the volume, you look at some of the problems of expense, and you look at the safety issues of it, my broad conclusion, and I'm not trying to really sell things too much on this, I'm trying to present stuff as an interesting overview of it, but on this particular one, my broad conclusion is that large-scale sequestration of carbon dioxide is pretty impractical. And yet, it's being discussed on a fairly regular basis on many multi-billion-dollar programs. So, science policy is being made and being discussed on a regular basis on topics just like this. And these sort of basic information seems to be being completely ignored by almost all proponents on both sides. You do this basic arithmetic, and it's It's grade school arithmetic with some big floating point numbers is all it is. And you work your way through it and you come to these sort of conclusions. And that type of thinking is what I'm trying to say, you know, I think, you know, more and more people should do it, and I'm just trying to encourage my captive audience, captive young audience tonight to do that sort of thinking as they go forward.